Thank you very much. My name is Oliver Sturm. Some people call me Ollie, and I'm here to talk about advanced pattern matching in C Sharp today. I have used C Sharp myself ever since it first came around, very long time, and I'm today talking about the features that have evolved there to make the pattern matching feature set what it is today over many different versions of C Sharp. I have, these are three agenda items. As we've heard, we don't have very much time today. I will talk about some of the use cases that are not so obvious after getting into the basics, basically. And then I am going to look at the pattern matching feature set from the perspective of sort of a functional programmer, seeing how I've got some code samples that I took from Haskell originally. And I wanted to see if it was going to be possible to use the C Sharp pattern matching feature set to replicate what people might do in functional languages, primarily along the lines of this Haskell example. Right, so let's get into this basically. The pattern matching as a feature set has evolved for a very long time, and I've prepared just a few slides to get us into this and sort of level the playing field so we all know what the standard feature set is. In C Sharp 7, things began with this simple value is type T expression, which at the time was actually interestingly well regarded by many people, but people mainly used it for purposes of simplifying null checks and casts, right? Remember how this was when you had to first check whether a type was something specific with the old is operator. And then you still had to convert it in some other way by using as or a cast or whatever, and then maybe you were going to check for nulls, and all of that could suddenly happen at the same time. So that was quite an exciting new feature, even though we didn't entirely appreciate that that was the beginning of pattern matching as such. And of course, we could also do that in a switch statement. However, switch was still a statement which only changed when C Sharp 8 came around, and with it came switch expressions. So we were now able to actually also return stuff from a switch expression. And there were a few other items, like, for example, the ability to use exceptions as part of an expression instead of just a statement, and so on. And we gained the first of the supported pattern types that are exciting today, the property pattern and the positional pattern. I think for a short while it was called the tuple pattern back then, because we didn't really have too many other ways of using positions at the time. That changed later on when deconstruction also became supported. So I just added it on this one here. And in C Sharp 9, there was quite a lot of stuff going on. We had the logical and relational patterns coming in. I'm going to show a couple of short examples in a moment. Structural enhancements as well. So you were able to put parens around parts of your patterns and that sort of thing to make them more complex. So in C Sharp 9, it became possible really to handle lots of complex structures of data very efficiently using patterns. In 10, we just had a small little feature coming in, nested property patterns, where you were able to basically have a property path as part of a pattern instead of having to go into various levels of a hierarchy. And then finally, in C Sharp 11, we had the big missing thing in many ways, the support for list patterns that came in, which is interesting, again, from this functional perspective that I was talking about earlier, because in particular in functional languages, patterns for lists are very often used in conjunction with recursive algorithms. So that's like a very common thing, and it was a big missing part to the pattern matching feature set in C Sharp. Now, nothing more happened since. We'll see what happens next. C Sharp 12 and 13 have not forwarded this. There are still a few small things missing, but nothing super important. So let's have a quick look at some samples here. The first thing I have is basically on the state of C Sharp 9, not to take up too much time with those basic feature demonstrations here. In C Sharp 9, we were able to write constructs like this, which is altogether quite complicated already. And just in case some of you might not be familiar with the idea of pattern matching at all, we were able to use the switch expression where we have the value, the variable that we're switching on right in front there, followed by the switch keyword, and then this curly brace block. And then we have individual cases, like each line here is a case, right? So this is the match expression right there. And in this case, we're matching positionally. We have two elements in the object that we're matching. The object order, by the way, is in fact, where is it now? Here it is a class that has a deconstruct method on it. But the positional pattern match down here could work in exactly the same way with a tuple, right? So that's why the syntax kind of looks like a tuple as well. We can use labels if we like, which is not necessary, but it can be done. And in this case here, I've chosen to repeat my label, or not to repeat my labels. I'm only mentioning them one time on the first row of the match, where several other matches use the same structure, but they don't have labels because it seemed unnecessary to repeat them every time. Yeah, so then we have the ability, of course, to match explicit values, but in this case, we're using relational operators to say this value should be smaller than 0, for example. And we're using placeholders like with the item price here, because we don't care what this value contains, actually. These are error conditions that are being matched first. And after that, we're matching values again and then returning results, which are enum values in this particular case. Yeah, so that's more or less what's in here. Finally, we have this feature down here where we're actually extracting information from the matched object using the var keyword in front. So we have variables C and P available now within the expression. And I'm not using them in the return. The return is just an enum one more time, but I am using them within this guard here that says we basically have a condition attached to the match for some extra filtering, if you will, right? So that summarizes quite nicely up to the status of C#9, the features that pattern matching had. And in 11, as another short example, we had the list matches in here. There are numerous examples in the code here. I have a link to the code at the end if you'd like to play with it yourself. So you were able now to match lists of data, including ones that have placeholders, like in this case, the spread operator, to say we don't know how many other elements might there be at the start of the list. And we can also combine these features, for example, by adding a relational operator in this particular item in the list. And then we were able to split the list into parts here. Typical functional thing, now we're kind of getting there. We're splitting into a head element and the tail element. So that's like one X and multiple X's. Right? That's a very typical way of referring to these values. And that allows us then at this point to write functions in this kind of recursive style that is very commonly used in functional languages, where we match to find if the list is empty, in which case that's the end of the recursion. And if it's not empty, we're going to split it into its parts, the one head part and the remaining tail parts, and then do some calculation over that. Right. So yeah, that does not solve, all the problems of using recursion in C#, but it is a quite elegant way of representing an algorithm like that. And it can also be easy to port algorithms this way from functional environments to C#. Okay, so that's just, the standard feature set. Now, moving on a little bit in the slides here, I've got a couple of examples, or there are 4, in fact, for less obvious use cases. First, the ability to construct tuples on the fly. This is just a small thing, really, but I remember it had me baffled the very first time I saw it myself, so I thought I would show you that quickly. The possibility to replace ternary expressions, because for some reason, some people really hate ternary expressions, right? I kind of like them myself, but it is possible to use patterns instead, and I do that occasionally, so I thought that was interesting too. The ability to combine different match patterns, that is not obvious at all, and it is something that I've used to good effect in some of my code. And finally, a pattern to deal with the comparer of t implementation, which I thought was interesting since that has been around quite a long time, and there wasn't ever really a good syntactic way of dealing with it so far. So let's have a look at these examples. I'm going to go to this implementation here, where this is test code that you're looking at, which is not totally relevant what it does at all. It's a compare function that basically says, if we have certain values here, then we regard them as equal or not equal or whatever. The pattern used here, by the way, is the same that I was just referring to with the compare pattern, where you say if the first value is considered smaller than the second, then we return a negative result. If it's greater than the second, then we return a positive result. If they're the same, we return zero, right? Like that. But the thing I wanted to point out here is basically just this bit right here at the beginning. You notice that the compare function receives two separate arguments, string x and string y. And when I first saw a pattern like this somewhere in the documentation or whatever a very long time ago, or in somebody's sample code, I kind of thought, oh, that's exciting. So somehow the switch expression actually has the ability to work with multiple values if I just kind of put them in parens and pass them like that. And that was, of course, not true. It doesn't do this at all. What actually happens is simply that the syntax constructs a tuple on the fly for me to match against, which, gives you the same result. I can now match both values in combination, as I'm doing here. It reads very intuitively, but I thought it was an interesting find after I discovered what really happens there, because my original impression of what might have been going on there was actually quite different from what was really happening. So that's exciting. Right. So the second one of the items I'd like to show you is in the file either. Let me find this here, or either, depending on your particular persuasion. This is the example about potentially replacing ternary expressions. You see, so in a case like this here, I've got this little helper here, from right. This is part of some functional code that I once wrote for a book about functional programming in C#. And I'm receiving a default value and also an object of this type either here, and I'm matching on the either element. And if this is a certain type here, then I'm using a value out of it. Otherwise, I'm using a default value. So this, of course, could be represented by a ternary expression quite easily, but I have chosen not to do that here. And I believe actually when I first wrote this, I was kind of doing a lot of things with pattern matching. You can see some more, in the code down here, where it just seemed to make sense to continue doing things with pattern matching. And I only realized later that it was not exactly necessary in this case to actually use pattern matching. But then I thought, well, that's actually exciting. Perhaps people would like to do this for consistency, because, once you start doing things with patterns, it kind of becomes a thing you can get used to quite easily. It might also potentially be more easily extensible if you're thinking that the algorithm could maybe not stay that way forever. And of course, again, some people really hate ternary expressions. It is perhaps a little bit easier to format a block of pattern matching code like this, so that the two cases that we're dealing with are listed line by line like that. So, your mileage may vary, as they say, but I thought it was an interesting example here to use patterns this way. Now, a little bit more exciting is the example in, let's see, this is this file right here. That's the one that was also on the slide, in fact. And this is the example that illustrates how you can combine different pattern matching techniques. In this case, again, I've got this type here called either, and this is basically like a result pattern sort of thing. So we have right of t, as you can see here. This is one of the options for the type that I might receive here. But there is also a left of t uh, derived type that comes from either just as much as the right of t does. Now, the left of t has a type parameter t. Maybe I should refer to it as L or something for clarity, because the right of t has its own type parameter and they're not the same. So I could argue that any particular either value can be either left of L or a right of R, if you will. And in this case of the bind function here, I don't really care what the left type is. You know, the result pattern, your left type is basically what happens when something goes wrong. So it could be an error message, or it could be an exception type or something like that, right? It doesn't matter. And that's exactly the point. Now, in this case here, I don't want to write my bind function to receive two generic type parameters, because I really only care for the one that represents the correct situation and not the incorrect situation. In which case, I can combine patterns. So this here simply uses a property pattern to say, if my either has a property on it that says it is in fact a left value, that is an error value, then we will just return that value. And on the right side, on the other hand, we need to access the value that is inside the object and therefore we need the t type parameter for it, right? So this is a monadic bind function, by the way, in case anybody thinks that's an exciting detail. Okay, right. So that's interesting. We can combine these types of matches, the property pattern, for example, with the type match here and so on. You can also come up with other combinations if you like. So that's an interesting detail, I believe. And then finally, I've got one more example for the, or get to that in a moment, for the comparer match that I was talking about. So if we have this comparer of t, d4 compare kind of thing here, we get information back, just like I was telling you before, where we have smaller than zero, greater than zero values and so on. And now I can match those like so. And that was never the case before. It required a few different, if, else, and whatever clauses to do this. And as a result, I think that is a little bit of an interesting tidbit on the side. Right, now let's get to the really exciting stuff, because we're already running out of time. Well, not quite, but we're getting there. As I said, I was very much into pattern matching in functional languages, and I've got a couple of examples with me here for that as well, where pattern matching is used. For example, here we have pattern matching in the language Erlang. Which some of you might be using Elixir today, so there is a similar structure. There are similar structures in there since it is based on Erlang. So we have a pattern right here where we're basically matching a thing called an atom. This is the add or mult atom, and it contains a couple of values, A and B. They're the capital letter ones in Erlang, never mind. So this is deeply embedded in the language itself to be able to use this. In languages like Haskell, we have pattern matching that allows us to declare overloads. So an overload in Haskell can have its own pattern. So this one says if certain foods are equal, then we consider them equal. And on the other hand, if that we have a fallback case, if none of those match, then we return false. So each of these lines is basically like an overload in Haskell. There are other examples here where we can also do things like matching against a relational pattern, if you will. They have an otherwise keyword in Haskell, which I think is kind of cool anyway. I like otherwise. Or we can use examples, like in this case here, where we simply say, again, define multiple overloads by way of a pattern match in order to make our logic. And of course, in F sharp, just as an aside, there is matching in there as well. We saw the presentation about active patterns, or that involved active patterns, just a little while ago. So there's a lot of cool stuff like this going on. Now, when I wrote this code that I was just talking about with the functional C# code all these years ago, that was on the on the state of C# 3 initially. That's a very long time ago. I implemented a feature in it, that in this library, that has a red-black tree implementation. And the Haskell code that I used as the basis of this is this here. So we have this thing, it was called a red-black set there. That is a discriminated union in Haskell, by the way, which is kind of cool. Maybe we'll see that in C# soon enough. Not yet, right? But this is how it was implemented. And it has this function called balance that balances the nodes in a red-black tree. If you guys have ever implemented one, you might be familiar with that. It's complicated, that's the point. And I had this existing functional algorithm that already did it. Now, of course, it was a little more complicated to do the same thing in C# at the time. Let me move to this other project here. So here is the implementation. Actually, we can get rid of that so it kind of fits on screen, right? If it does, this is a screen full of dense code that represents the exact same logic. Here it is again in the comment that I previously had in Haskell, where it takes, 5 lines, right? Basically, this here, that's the balance function in Haskell with all those patterns inside. And that's a lot, I don't know if you consider it easier, but it's definitely shorter. And what if I made a mistake trying to port this code here to C#? Then, of course, I'd be quite out of luck with this implementation down here, because while it might read okay to a C# person, it's definitely not very easily maintained. So for all those reasons, I got interested to see if the current C# pattern matching feature set would actually allow us to kind of do the same thing as we do in Haskell with those patterns in C# now. Microsoft did not talk much about this kind of thing in their documentation, which is fine, right? They focus on other stuff. So let's see. I've got, first of all, just quickly on the final screen here, I've got a number of tests running in this setup here, and they're all green right now. That's really the only thing, right? If I end up removing this code, which I will do right now here, there we go. Let's just delete everything from the balance function and then save. And we should see that this goes red, right? Okay, so now, of course, we've totally broken it anyway, just to make it clear what's going on here. Now, we really don't have very much time, so let me grab a snippet here, because that's otherwise going to take a little too long to type this right now. Let me copy this, and we can drop this in here, and I'll just say a few words about it. Actually, let's remove this for brevity. So we have a couple of constant values, which is kind of the same as we have in Haskell, where the black and the red nodes are represented by a short r or b, right? That's good for brevity. And I've also got a little helper that I call TT. You see, in Haskell, the tree itself has the name T, and so I call it TT because I already use T for a generic parameter. This is a helper that constructs a new tree, because that's what happens every time on the right-hand side of these expressions. This is the construction of a new tree. And now, if you compare what it says down here in this crazy-looking switch expression to the Haskell, you will see that this is actually equivalent to that. Okay, so let's see. We're starting with the match on an individual B, that's here. And then we have a red tree underneath, which is this one right there. And there's a red tree in there again, which is this one. And then we're extracting the values in Haskell. That's like easy, like this, A, X, and B. In C#, I need to use the var keyword every time, which makes it a bit longer, but the logic still remains the same. And then on the upper level again, we're also extracting the other values, X, Y, and C, and Z or Z and D, right? So they are extracted. So the structure of this expression is in fact the exact same as it was in Haskell now. And on the other side of it, we have the construction expression that is also the same exactly as we had in Haskell. Now, that is something that you don't easily find in the documentation, that this kind of complicated nested structure is supported and whatever else. I mean, It's quite obvious, really, but I had to play around a bit to figure this out. Let me save that and make a final check here on the other side. And hey, my tests have gone green again. There they are, right? So that works. The logic in this balance function remains the same as it was before. Now, when I present this, I often get questions, do you really think this is better now? Good question, better or worse, right? But it does definitely serve the purpose of porting the code from this other language that is heavily based in pattern matching. That makes that a lot easier, and it also makes it easier to spot if there were any problems, any issues where I entered the wrong variable name, perhaps, or whatever else, because the syntax is now similar enough. And for me, it also served just to satisfy my curiosity about the actual functionality of pattern matching in C sharp. So we can quite confidently claim that it is practically as good as it is in Haskell. Okay, that's it for me. I have only a couple other slides here with resources. There are a couple of links on this one if you're interested in checking out the code that I showed today here. And of course, download dotnet 9 if you haven't done that yet. That is everything from my end. Thank you very much.